Well, before the spring break, we already started talking about artificial intelligence and more specifically, deep learning and its impact to a lot of fields. As you can see, in the recent decade, we see how artificial intelligence has progressed in multiple fields, including games, right? That's a perfect test bed for Turing test, right? Including image or computer vision tasks, including text, right? Natural language processing. And the early waves of computer vision or natural language processing products have already shown their impacts to the healthcare field, right? Of course, there are also fallbacks, right? We know IBM Watson and also that it started collaboration with MD Anderson quite early, but also we saw that the outcome isn't, as perfect as we anticipated, right? It's not like the fairy tale, right? After that, AI and healthcare are married happily forever. It's not like that, right? This shows the challenges that are remaining, as well as more foundational AI changes. You cannot just do AI to healthcare. Healthcare inspires a lot of AI for healthcare. So let's bear those in mind, and then we'll start talking about, this week, artificial neural networks and computer vision, especially image data. And the representative neural network is CNN. So we don't assume that you know anything about neural networks. But also, if you have already learned about neural networks, right, many of you have already, again, I want you to think about them from the perspective of optimization, what are important for neural networks, as well as understanding neural networks from not only the intuitive illustration, like those neurons and the connections, but also the mathematics, and as well as programming, okay? So that's what we will try to address. And at the end, we'll include 2 case studies. Again, it's about protein structure prediction. But you see that the formulation is very different, and the way the problem is solved is also very different. And you may ask yourself, why are these problems? Why is the problem of protein structure prediction can now be formulated in this way? What images are there, and what are we utilizing? Okay. Okay, so let's get started. I think at the beginning of this week, we'll mostly talk about this neural networks, and then we will branch into the convolutional neural networks. Okay, and then we'll spend quite some time on the math and underlying of CNN, and in the end, we include a couple of case studies. Okay. So let's talk about neural networks, right? So as you have learned before, right, deep learning is actually the poster child of artificial intelligence. A lot of people say that I'm doing AI, but essentially it's deep learning. Okay, AI is a buzzword, but we also knew that from what you learned before, AI is much wider than machine learning, right? And so what is machine learning, right? So what is machine learning? I think this is a good comic, right? So you have the data feeding into the models, and within the models you have a lot of operations, mathematical operators. In the end, you make a prediction, right? And this is actually a very funny comic if you read into it, right? That's machine learning. And we knew better that, for instance, from the perspective of regression, what we care about is not how the model fits observed data. It's actually about how the model could predict for the unseen tested data, right? That's why we had the bias variance trade-off, right? So if you look at machine learning, it's actually, it's it's very wide concept, right? So if you look at this principal axis of deep versus shallow, we have already learned a lot of shallow machine learning models before. We talked about support vector machines. We talked about the boosting, including AdaBoost. We'll briefly mention the single layer perceptron before we talk about the multi-layer perceptron this week, right? But these are supervised machine learning that are, shallow. They can be deeper, right? Using neural networks, convolutional neural networks, or recurrent neural networks, or language models. This will be described. But also you can think of it from another perspective, that is whether it's a supervised versus unsupervised, right? In other words, whether there are labels being utilized in this machine learning, right? So in the unsupervised shallow models, right, we have some early forms of neural networks, such as the restricted Boltzmann machines, right? Or the shallow autoencoders, or the Gaussian mixture modeling, right? So those are shallow, unsupervised models that you might have learned. Right? The deep ones are including this deep autoencoders or GAN, right? This will be learned at the end about the generative models, right? Deep belief networks or Bayes neural networks and so on. So this is a rough idea about what is the landscape of machine learning, right? And you have to see that we've previously covered this, and now we are going to the deep side of the supervised machine learning, right? So deep learning, right? Deep learning. It's not, let's put it in this way. Neural network itself is really an old concept, right? But probably early days we utilize just one hidden layer between the input and output layers. Okay, a lot of reasons. Not just the fact of the hardware, but also the fact of solving these problems. Actually, I will revisit this again. Just keep in mind that these machine learning problems are optimization problems. In the end, you need optimization algorithms to solve these optimization problems, right? So it's not like, I can draw more layers and then there are algorithms that can readily solve the problem. Okay, it takes a lot to go from the single to multiple hidden layers. It's not a conceptual change. You see what I mean? It's not like nobody can visualize multiple hidden layers. That's not the problem. The problem is what can support this model, including the hardware, including the software, specifically solving this optimization problem, okay? I wouldn't name the technique, but you should know what technique I'm referring to. I'm gonna ask again in today's lecture, or when we talk about a multiple-layer perceptron. I think it should be today. In this example, this deep learning neural network is a computer vision kind of task, right? You have an image input, and the output is like a classification who this person is, right? George. So you can see that what's really interesting about this deep learning neural network is that what at different layers, what are picked up, what parts of the images or what signals of the images are picked up by different layers, right? Because you can see at the beginning, right? It's just about each pixel and how light, how dark it is, right? That's at the input layer. But the intermediate neurons are picking up different things, right? Like edge detection or combination of edges or more sophisticated features like eyes and nose and so on, right? So in signals and systems, you have learned before that we can actually manually design the filters to detect, for instance, edges, right? Right? So we can make sure that, for instance, a filter that takes the difference between two neighboring pixels, and that is one way for edge detection, right? You have the horizontal or vertical edge detection, right? So there's a lot of ways for you to manually design those filters from principle, right? But in this case, you are actually automatically learning much higher dimensional and nonlinear filters that are capable of detecting much more sophisticated features. So that's a difference, okay, compared to the earlier signal processing. So one is principle-driven and one is data-driven, okay? And let's start talking about neural networks, right? I'm going to make this claim. You have already learned some neural networks in this course already. Well, you can say these are special cases, right? Okay, so what have we learned? What neural networks have we learned so far? Can you recall some? Have we learned any neural networks so far in this course? Yes? No? Have we learned any neural networks yet? SVM? Okay, great. Thank you, Nami. SVM is a neural network. Good. We'll show more about that. Good point. Anything else? Something even simpler than SVM. Yeah, a little simpler. Also for classification. We talked about it like 2 weeks ago in diagnosis. Logistic regression. Okay, so I'm going to show you what I'm talking about, but then I want you to also keep in mind that machine learning is about formulating and solving optimization problems. So I want you to keep in mind that when we're talking about these machine learning neural networks, what are the elements important for these models? Okay? From the perspective of optimization, what elements are important? Decision variables, constraints, and optimization. In the end, there is an optimization algorithm for the corresponding formulation, right? I want you to keep those in mind. So again, when we talk about the first example, linear regression, okay? I want you to think about it as optimization problem. So what are the elements important? First, there's a data and there's a model, right? So the data are the paired x and y, right? Input and output, right? So this is for any arbitrary xi, I have the y hat, which is the prediction. So this y hat is not bold-faced, indicating that it's a scalar, and x is bold-faced, indicating it's a vector, and the w and x are bold-faced and lowercase, indicating that they are vectors, right? When we have the bold-faced uppercases, we indicate that this matrix, okay? So you can put a subscript I here to indicate that this is the ith example, right? But if you consider all the data, all the pairs of xi's and yi's, we have this expression, right? This is lumping everything into linear algebra, we have this y vector of all the observed labels equal to capital X, W plus B. And the decision variables are W and B, right? Okay, you can even put 1 into this X feature, right? And then W is enough for all the decision variables, okay? Now that you have the data to fit and the model, right? So this is a model, right? Next question is, what is an optimal model, right? So for optimality, you need objective function. So the objective function here is, again, summed over all the example i's, right? And for each example I, this loss L is a function of W and B, the decision variables, right? And what you see here is the W transposed xi plus B minus yi. So this is this error, right? This is just the error and then squared. So in other words, this is like the mean squared error. Right? There's 1/2 there, which is a constant. And I think we put it there usually for elegant expression of the analytical optimal solution, okay? So that in this case, your Hessian is just something related to W without having to consider this non-one constant. Okay. Okay, now that we have the data and the model and we have the loss, and you probably will include the regularization as well, okay? You probably have to include the regularization. Here, this is just the mean squared error. And then once that is done, we have to solve this optimization problem using some optimizer. We know already that this is something with analytical solution already. If your regularization is L2, that's something that we can solve analytically as well, right? Because it's a quadratic optimization problem. If the regularization is L1, we are still facing a convex optimization problem, but we cannot count on gradients. But first of all, we don't have the analytical solution for the optimum. Secondly, we cannot count on the gradient-based algorithms, right? Why? Because the gradients are not continuous, right? Because of the absolute value of W. And if your regularization LP norm has P between 0 and 1, then that optimization is not even convex, right? Right? Keep in mind, that's what we taught you before, okay? All right, so that's from the perspective of optimization, right? So you can see that this can be already represented as a one-layer neural network, right? Let's try to see that in programming, right? Because I feel I'd like to show all this programming in NumPy because I feel like with a lot of libraries, you just you feel like all this symbolic expression of a neural network and the losses, and sometimes you just forget about what's behind it. I think I'd rather use a numerical Python to show it right here, okay? One thing I want to emphasize is that why we would like to use this kind of expression, because you have to think about one of the reasons that deep learning got popular and successful. That's because of what? The operations are relatively friendly for GPUs. What kind of operations? This kind of linear algebra operations, right? A lot of parallelization can be done. Think about how many threads are there within a GPU core, right? So a lot of things can be parallelized. So in this case, you don't want to write something that's just a sum over all the example i's like this. That's not a good idea, right? So what you want to do is somehow make it, scalable, right? Easy to compute. So in this case, for instance, this is how you define a model, which is a linear regressor, right? So you are using the dot product of the X matrix and the W vector plus B, right? Remember that this is over all the examples, I from 1 to n. Well, if you talk about the squared loss without the regularization, for instance, in this case, right? Again, you have y hat minus y reshape, y hat reshape, y hat shape, and then squared, and then divided by 2. Again, I'm using linear algebra expression. I'm not using scalar and sum or anything. All of this are for the linear algebra scalability, okay? Lastly, what about optimization? As I said, you essentially, if you are just looking at the squared loss, there's already analytical expression of that, right? But usually we have other losses. And we have to count on gradient-based algorithms. We'll use one lecture to dedicate to optimization in deep learning. But here, let's say we're considering the gradient descent, right? But it's not like the traditional sense of gradient descent in the sense that you are looking at the stochastic gradient descent, right? So in other words, because of the big data issue, you have a lot of training examples, right? And your models might be large as well. Your parameters can be large, right? And then there's a learning rate that is a hyperparameter that you can tune. So in this case, what if we split our data, right, into a lot of batches, right? Well, within each batch, we have something that we can handle, both for the time complexity and the space complexity, right? Especially the space complexity, if you think about the memory. Time complexity, if your model has a lot of parameters. It takes a long time to train. So in other words, I'm just looking at the loss calculated over the current batch, right? And there's a way to calculate the gradient of the parameters in this stochastic sense, right? And then we keep updating the parameters, right? We keep updating the parameters. So this is how you compute. So again, I'd like to keep these two views side to side. One is the math, one is the Python programming. Okay, so let's make sure that you both understand them mathematically and are able to program them, to implement them. Okay, I think this scalability issue is very important. Okay, but now with the math and the coding, right? Now we can see them as what you usually see in illustrations, right? So again, we are looking at the linear regression. So you have these input layers, these input neurons, right? With D. D is the dimension of what? Features, right? Or attributes in this case. And for each attribute or feature, you multiply it by Wi. And you have the sum, and then you have this logistic function. This is a linear regression, by the way. Not logistic yet, just a linear, okay? So it's just a linear regression in this case. So this is the illustration of what we have talked about so far, about math and the coding. Now we can move on to more sophisticated, from linear regression to logistic regression. Now let's make logistic regression a little bit more general, more than just binary classification. Let's look at multi-class classification, right? Again, you have a O, which is output, which is WX plus B, which is again linear, right? Which is again linear. But then you use a softmax function over O to get the ultimate output Y hat. So this Y hat is essentially, as you can see, for each example I, what Y hat is this exponential of OI, this output of, for example, I, divided by the sum of example of the exponential of OJs. So this is a softmax function, right? So in this case, these I's and J's are the dimensions for the labels. So if you have K classes, J goes from 1 to K, okay? And then you can vectorize them. So this is a multinomial logistic regression, which is essentially a linear regression, but then plus a softmax for classification, okay? So this is the data in the model, and what is the loss function? The loss function here, as we have explained before actually in the diagnosis, right? What we are trying to maximize is the likelihood. The likelihood of observing Y given the input X and the W's, okay? I should put a semicolon W's. But essentially, if you treat all the examples I's, right? I put a superscript I with a parenthesis here, indicating that this is I's example, okay? This I is I's label class, don't get confused, okay? Here I didn't indicate which example it is. I used the generic X and the generic Y hat. I didn't use any index of the example, okay? So the index here, I in the subscript, and the index here, J and I in the subscript, indicating the output for the label class I or J, okay? And here I put a superscript here to indicate that this is example I from 1 to n, okay? So don't get confused here. So if I assume, again, that these examples are IID, are, independently and identically distributed, actually I only used independence here, then I can rewrite this probability as a product of individual examples' conditional probabilities, right? And then and then I can write the loss function as minus log, that I can maximize this loss function, right? Then log of the product becomes the sum, right? And then we can rewrite them as yj times log of the y hat j, where yj is the the ground truth or the observed label for example x. This is the observed label for class J. Okay, again, this is a class. Don't get confused. Okay, here for simplicity, I didn't put the superscript I here to indicate that this is example I. But for any examples, okay, I can write them in this way. Right? So what is this? Again, y hat is the probability for this example in class J. Right? So what we are writing here is what? Is nothing but a multi-class cross entropy, isn't it? Right? So, and then you can add this over all the example i's. Okay, this is L for the example I. So the optimization problem is to find the optimal W star, right? This W parameters here. So that we can optimize the L over all the examples, right? So over all the examples. So coding-wise, let's see what it does, right? So we have W that we can randomly initialize them to be a normal distribution with 0 mean and 0.01 standard deviation, for instance, right? This is how you initialize your parameters, right? And you can initialize your W to be zeros. There are different ways to initialize your parameters, right? This normal distribution is what is something related to what Javier, XAVIR Javier initialization is doing, right? Using a random normal distribution with 0 mean, okay? A white noise, basically. Some other cases use zeros. When is it better to use Javier initialization? When is it better to use zero initialization? Depends on your layers and depends on your activation functions. I suggest you to look into a lot of articles about it. It's more like experiences or empirical observations, right? And let's look at the softmax, for instance. In this case, again, I want to show you that you want to vectorize. You want to vectorize your mass expression and make sure that your implementation or coding is scalable, right? So if you vectorize, for instance, in this case, you see that you now, instead of a single observation O, right? Now you have a matrix O, right, equals to X times W plus B, right? And then Y hat is now, instead of a single scalar for one example, now is a matrix. I'm sorry, instead of a vector, excuse me, because you have K classes, right? The length of Y hat for one example is 1 times K or K times 1. And then in this case, if you look at all the examples, then Y hat is now a matrix, right? Again, uppercase, bold-faced. And it's a matrix which is a softmax over the big O matrix, right? So if you think in this way, you can see that the way you implement a softmax is the following. First of all, it's over the X matrix, right? Right. So this is, this X exponential, which is the exponential of this is the numerator, right? And the partition function is the denominator, right? Right? So it's summed over x is 1, right? Because it's summing over all the exponentials, right? And then you return the numerator divided by the denominator. So that's again what's the definition of a softmax, right? And then let's look at this network, right? Essentially, it's returning what? It's returning the softmax of what? Well, it's a softmax of O, right? So we need to give O there, right? Right? What is our O? Our observed output, a neural network output, O, right, is XW plus B, right? So what you do is like what you have seen before in the last time, using a dot product of the W matrix and the X matrix plus B. But you got to be careful about this reshape -1 num inputs. Okay, you got to be careful about this one. Got to make sure that what dimension is multiplied to what dimension. This is very important. If you don't fully understand this, I strongly suggest you to look into this much more carefully. Okay, because you have to control, you have to understand the math and you have to control the dimensionality, right? A lot of the errors can occur there, and we cannot count on libraries to do everything for us, right? And lastly, the last function. The last function, as I said, is cross entropy, right? And this cross entropy is in this expression, right? Again, I'm considering not just one example, and in my cases, these are vectors for all the examples, and then I'm returning this value, right? So this is how the cross entropy is defined for a single example. And then when you are calling this cross entropy to maximize this loss function for all the examples, you're going to make sure that you give the correct y hat and y, right? In your case, it's going to be a vector, and you're going to make sure that you're going to use the products or sum very carefully, okay? Any questions so far about these two examples? They are very simple, but there's a lot of things about them, all right? If you want to now think about them as as neural net works, right? And then you need to understand them with regard to the optimization formulations, these three elements, as well as the scalability in the programming. Make sure that you have a deep understanding of this, okay? These are just very simple neural networks, okay? Any questions so far? Any questions? Okay, now let's move on. Again, as I said, you could represent them now, illustrate them as this multinomial logistic regression, right? So I have O's there, and I didn't put the softmax here, and you can add one more softmax layer, and the output is y hat, right? y1 hat to y3 hat, y4 hat, and so on, okay? Depending on how many classes do you have. Okay, so now let's talk about multi-layer perceptron. Let's start with a single-layer perceptron. Okay, perceptron is a very important concept in the early days of artificial intelligence, right? By Rosenblatt. Right, this is not just a model, but actually a real machine, a single-layer perceptron that was done in the 50s or 60s. Okay. So we will talk about the biological reasons or motivations underlying the single-layer perceptron in a few slides. But now I just want you to regard them as this very simple illustration, right? Because we already gone through the math and the programming to understand these illustrations, right? So this is a single-layer perceptron. In the early days, remember that this is sometimes people use this interchangeably with DNN, but this is for the multi-layer perceptrons. In the case of the single-layer perceptron, you can think of it as a linear classifier, right? Depending on how many classes you have. What you have here, these are just the intermediate outputs. Remember, in the end, my prediction is y hat, right? yi hat, where this example belongs to class I. Okay, the probability of the example belonging to class I. Okay, all right. So this is a single-layer perceptron. It's linear classifier. Could be multinomial, multi-class, and we can add one hidden layer between the input or output layer. Okay, like this H, right? And you can determine the width or the number of neurons in the hidden layer, okay? Well, now is a question, right? So let's ask this question, right? So if you keep stacking more and more hidden layers, right? Do you think that your model is much more powerful? Or do you think that your model is still limited in some way? So imagine that I want to empower my model, right? Going to the multi-layer perceptrons, and I can stack more and more hidden layers, right? Make it deeper and deeper. Do you think that this is making your model much more powerful, or do you still think that is limited somehow? It's still limited. Why?
I feel like adding, it's not the same, but I feel adding the layers are similar to what's that, like changing 1D feature to 2D feature with what's that name?
You feel like adding the more layers is as if we are expanding the feature dimensions without changing the operator over the features. Is that right? So let's look at one example, okay? In this case, we use two layers, right? Your O is W2H plus the B2, right? And then your H is the output of, is input to the second hidden layer, which is the output of the first hidden layer, right? So you can replace H by W1X plus B1, right? And if you rearrange them, you will find out that it's still in the form of Wx plus B, where W is this two layers W's product, and B is this affine function. So in other words, you can keep stacking the hidden layers, right? But it won't change the fact that your classifier is linear. Okay? Okay, that's one point to pay attention. Okay, this is one thing to think about. Another thing to think about is the following, right? Why do you worry about these linear classifiers, right? If you recall, when we talked about support vector machines, we said that, when you find out that the linear support vector machines are inadequate, what would you do, right? Right? So because sometimes there's no perfect way to separate two classes with linear classifiers, right? Then you may say, well, then I allow this soft penalties, right? I allow violation of these, red goes to the other side of the linear classifier, but I make sure that it turns into a penalty, right? Another thing we said was that you may also consider a linear classifier in the kernel space that is nonlinear in the original feature space, right? Something to think about. Here, this is one example, right? So it's a very simple operation we are trying to emulate, okay? So the natural process to emulate is AND or OR. So in the case of AND, right, so we have 0, 0, 0, 1, and 0, 1, 0 all giving us 0. And only 1, 1 give us a 1. So you can use a linear classifier to separate them, right? The same for OR. But for this exclusive OR, right, which is only one when these two are different, 0, 1 or 1, 0, exclusive OR, would you get the output of 1, white circles? So in this case, it's really hard for you to use a single layer perceptron, right? Right? There's no single, in this case, linear classifier. that can separate these two perfectly, right? So this was actually related to the first winter of AI, okay? So basically after the powerful perceptron, there are a lot of research into it, right? So in 1969, Marvin Minsky, if you recall the Dartmouth workshop, how this proposal was submitted, which people, Shannon, right, was one of them. Minsky was one of them, I was asking you, right? And Marvin Minsky, right, whose name is now in the MIT C-Cell lab, right, Computer Science and Artificial Intelligence Laboratory, he basically proved that, you cannot, train a single layer perceptron for this very simple XOR, exclusive OR function. So in other words, you think about, the ambition of artificial intelligence back then was to figure out how brains work in a quantitative ways so that we can empower machines to do something similar, right? But now it cannot even do something for exclusive OR, right? So that was, the beginning of the first winter for AI, right? So that was 1969 when Marvin Minsky and the co-author published their paper to critique on Rosenblatt's single layer perceptron, right? And it's possible that you can include more layers, right? More hidden layers to have multi-layer perceptrons, right? But not exactly the same multi-layer perceptron we're talking about so far. It's not like Marvin Minsky did not know that, if you include more layers, this may become separable. The real reason is that there's no optimization algorithm available for this multi-layer, this kind of perceptron. When was it eventually born? 1969, Marvin Minsky critiqued two perceptrons, or single layer perceptrons, right? Using this example, right, theoretically proved that you cannot even emulate exclusive OR, right? But it's not like they didn't know multi-layer perceptrons can deal with it, right? But why that was still not a saving grace? Why was it not that useful? As I said, there's no optimization algorithm for multi-layer, this kind of linear neural network available. It was officially born 17 years later, a Nature paper, and this algorithm is called what? You know it, and use it every day if you're doing deep learning. It's called backpropagation. Okay? In fact, backpropagation was not born in 1986. Actually, backpropagation was rediscovered later that actually it was even born before the book of Perceptron. It's just really funny, okay? So mathematicians can be really ahead of. But it's common that we see a lot of rediscoveries, okay? But so, history aside, so our conclusion here is that, first of all, right, to enable these multiple hidden layers, you really need optimization algorithm to support them. But in the meantime, you're still in a class of linear functions or linear classifiers, right? So that leads to what we know today as multi-layer perceptron, right? The only thing you change here is that instead of directly taking the output, right, the linear output, you take the linear output and do a nonlinear transformation, and that is called a nonlinear activation function. We'll understand why it's called an activation function when we talk about the actual neurons. But this is what the activation function is doing, right? So this H is putting a nonlinear transformation to W1x plus B1, okay? And then this H is fed to O, okay? This is just a single hidden layer. if you add more and more hidden layer, basically at the end of each hidden layer, right, the last mathematical operation is this nonlinear transformation, right, so-called activation function. So you can stack more such hidden layers. Now this model can be much more expressive, okay? So, and then if you assume a fixed width, the number of neurons, and then if you increase the depth, then you can mathematically prove that the power of the model is, growing in some way. It's very easy to understand. If you think about, what we are having here is actually using a lot of piecewise linear facets to approximate a nonlinear manifold. You see what I mean? Right? Right? And the depth is, something like the power. It's like the exponential term, like the power that gives you the number of such piecewise surfaces or facets you could have. Okay, so that is some way to quantify the expressiveness of neural networks, right? You're basically asking yourself, how many pieces can I have, right? So in this case, we have two hidden layers, and each of them is a nonlinear transform of the linear output, which is called activation function sigma. Okay. And you have a lot of choices, right, for your activation function, right? ReLU, sigmoid, right? This hyperbolic tangent, and so on. There's also, this other kind of choices, right? Like a swoosh, right? How do you choose them? And it actually needs a lot of knowledge about the neural network computation, right? So we'll talk about them when we get to the neural network computation. We're not talking about computation so far, right? Remember, in the end of the optimization, we talked about computation, numerical optimization, right? So some of this knowledge will be brought back when we talk about the neural network computation. But if you are interested in knowing them, the conclusions so far, you can read these blog. Again, if you directly click the link, it may not work because every time when there's a hyphen, somehow the PowerPoint converted PDF does not represent this hyphen correctly. It's using a different ASCII. So I apologize. So I hope you can simply replace those ASCII with hyphens, okay? Or Google this link. Any questions so far? Okay, so there's more. There's more because I was asking at the beginning, right? Have you learned neural networks? Now we know that yes, we have learned them. We have learned linear regression is a neural network. Logistic regression is a neural network. And then MLP, right, is a neural network that we haven't learned, but support vector machines, like Nami was saying, are actually neural networks as well. So this was a 2002 paper, 2004 ICML paper, right? So if you read this abstract, it's very interesting. We first study ways to control the capacity of perceptrons, right? Mainly regularization parameters and early stopping. Using the margin idea introduced with the margin idea. Remember, support vector machines is about the margin maximization. Showing that under simple conditions, a perceptron is equivalent to an SVM. Right? This is a very interesting, a lot of the proofs from that paper. But under some simple conditions, a perceptron is equivalent to an SVM. Moreover, under some assumptions, it also appears that multi-layer perceptrons are a kind of mixture of support vector machines, maximizing the margin in the hidden layer space. Okay. Very nice results. So if you want to improve your understanding of support vector machines and MLPs and see the connection of them from the theoretical place, I strongly recommend you to read this paper again from ICML. Okay. So these are the neural networks we have already learned, right? Now let's try to summarize artificial neural networks, right? But see them now from biological perspective. Recall, how AI as a word was created, right? It's about, modeling how humans think in a way that can enable machines to do something similar, right? So if you start with the smallest computing unit, well, arguably smallest computing unit, because there's more underlying molecular basis underlying this nucleus. But if you're thinking about a single brain cell, right? In this case, right? We have the nucleus, right? We have the cell body. We have the dendrites that making connections, right? And then these axons, right? These impulses are then carried away from the cell body and then going through the branches of axons and then reaching the terminals, right? So this is actually how neural network gets started, right? Why it's called a neural network, right? It's called for that for a reason. And then we are essentially using feed-forward neural network, right? Actually artificial neural network, but nobody is using artificial now because it's getting so popular. To emulate how a neuron compute. So this is a very simple model, right? This is a very simple model, right? So this could be the input axon from another, right? A neuron, the input x0, right? And then reaching the synapse, right? Parameterized by W0. And this could be a linear relationship, right? Then there could be axons from other neurons, right? Or other axons. So there are different input x sub i's, and they are weighted sum and reach the cell body. So that's the linear weighted sum. And then it's non-linearly activated. That's your sigma function, right? This f is the sigma function you have seen before. This is the classical feed-forward neural network, right? If you look at how this neuron is defined as a class, and then forward neural network, feed-forward neural network, is a function defined for this class neuron, right? So we basically have the cell body sum, which is the sum over all the inputs, right? Times the self weights, right? Plus the self bias. Weights are W, bias are B, right? And then there's some firing rate, which is essentially a sigmoid activation function, right? Then you return the sigma of this linear function. So that's really the foundation or the motivation and as well as the mathematical foundation for feed-forward neural networks, right? Okay, so now we know that why we say this is a neural network, right? Right? At the beginning we said that we want you to understand these concepts, neurons, layers, and activation functions, right? So I think that's a summary of what are they in the neural networks. But I want you to see them as something very natural, because if you look at how AI as a word or a field has been born, you will see that, well, that's a natural choice, okay? Okay, so far, any questions so far? We talked about the first take on neural networks. We talked about the basic concepts, neurons, layers, and as well as some special cases, right? Neurons, layers, activation functions, as well as some special cases, like linear regression or softmax regression or multinomial logistic regression, as well as MLP, right? We also said that support vector machines are also equivalent to perceptrons. So MLP is a mixture of SVMs.